Okay, so are you ready to dive into some seriously cool science today?
Always up for that. What are we looking at?
Fusion power.
I like where this is going.
We're going deep, straight to the source. Research from the Joint European Torus.
The JET.
You know it. Fusion, it's like the holy grail of clean energy, right? And we've all heard that. But like, what are they actually doing in those labs?
Yeah, what's the latest?
That's what this is. We're cracking open a paper. It's from the 22nd Topical Conference on Radio Frequency Power in Plasmas. It's a mouthful, but...
Sounds intense.
It is. But here's the thing. There's this one finding about hydrogen fuel.
Oh, interesting. Hydrogen, crucial stuff.
You'd think more fuel, more fusion, right?
Yeah.
Makes sense, right?
Seems logical, yeah.
Nope. Sometimes less hydrogen equals a more powerful reaction.
Really? Now that's counterintuitive.
Totally. So how does that even work?
We're talking about serious forces at play here. Superheated plasmas, different heating methods. It's a wild dance of energy.
They're using like high energy booms, right? To blast these atoms.
It's neutral beam injection, NBI.
And at the same time, they're hitting them with radio waves.
Right. Ion cyclotron resonance heating, ICRF.
So it's like cooking, but instead of an oven, it's a nuclear reactor.
Kind of, yeah. A very, very precise kind of cooking. It's all about finding the perfect recipe, the sweet spot where fusion really takes off.
And hydrogen is like what, the secret ingredient?
In a way, yeah. Too much. And it's like adding too much salt to your dish. It throws the whole balance off.
So you got to get that hydrogen just right. But how does that actually affect the fusion reaction?
Think of it like tuning a radio, trying to find the right frequency. Too much interference and you just get static.
Yeah.
Hydrogen, in the wrong amounts, can be like that interference, preventing those fusion reactions from happening.
So it's not just about brute force blasting those atoms with as much energy as possible.
Not at all.
It's about finesse.
Exactly. Finesse. And that's where this research gets really interesting. They found that when you get that hydrogen just right, it doesn't just affect the overall heating of the plasma, it specifically gives this boost to the deuterium.
Deuterium, that's another fuel source they're using, right?
Exactly.
So less hydrogen equals what? More energized deuterium?
It's like giving those deuterium ions a VIP backstage pass to the energy party. Technically, they call it a high energy tail in the deuterium distribution.
High energy tail, that's what they call it in the paper.
Straight for the scientists.
So some of this deuterium is suddenly hopped up on cosmic espresso.
Something like that. It means they're moving much faster, way more likely to collide with each other and fuse, releasing even more energy.
And that's why they're seeing these record-breaking numbers, right? Because of this high-energy tail.
It's a big piece of the puzzle, definitely.
This is blowing my mind, and we're just getting started. Okay. So we've got this super-powered deuterium. Fusion is happening. Everyone's happy, right?
So not so fast.
What? No.
Deuterium-tritium? That's what most people are looking at for the future of fusion power.
And this research, this is all about deuterium.
Right, but this research actually gives us some clues about deuterium-tritium fusion too.
Okay, so how does that work?
They looked at their findings, the hydrogen optimization, the deuterium boost, all of that, and they extrapolated.
Fancy science word.
Basically, they made predictions about how these results might translate to a deuterium-tritium fuel mix.
Because DT fusion, that's like the big leagues, right? Compared to DD.
Think of DD fusion as a firecracker and DT fusion as a stick of dynamite. Way more bang for your buck.
So even though they weren't actually using tritium at JTT, this research still tells us something about how to make DT fusion even better.
Exactly. It's like a sneak peek into the future of fusion power.
Okay, this is getting me really fired up about the future now. Fusion power, here we come. But before we completely jump the gun, there's one thing I'm still not clear on.
Okay, what is it?
Helium-3, they mentioned it in the paper, talked about comparing their results to some previous research on helium-3.
Ah, yes. Helium-3, the often overlooked cousin in the fusion family.
So is it like the forgotten hero of fusion fuels?
It could be. It's got some serious potential advantages over deuterium-tritium.
Okay, like what? Give me the rundown.
For starters, helium-3 fusion is even cleaner.
Cleaner than something that's already supposed to be like the cleanest energy source ever?
It's true.
Yeah.
DT fusion still produces a small amount of radioactive byproducts, but helium-3 fusion, virtually none.
Wow. Okay, so it's cleaner, but is it as powerful as DT fusion?
Potentially, even more so. And on top of that, it's easier to contain.
Hold on, easier? How so?
DT fusion, it creates neutrons. Those tricky little particles can damage the reactor over time.
So you've got to like constantly be repairing and replacing parts.
It's a constant challenge, yes. But helium-3 fusion, it mostly produces charged particles. Way easier to control, much less wear and tear on the reactor.
So to recap, helium-3, cleaner, potentially more powerful and easier to manage. Sign me up.
It sounds almost too good to be true, right?
What's the catch? There's got to be a catch.
The catch is helium-3 is incredibly rare here on Earth, like almost non-existent.
So where do we get it from?
The moon. We need to mine it from the lunar surface.
Okay, that's a bit of a logistical hurdle.
A bit, yes.
But still, it's exciting, right? It means there are other possibilities out there, other avenues for fusion research to explore.
Absolutely. And who knows, maybe someday lunar mining will be as commonplace as, say, offshore drilling.
A fusion-powered future fueled by helium-3 from the moon. It sounds like something out of science fiction.
It does, doesn't it? But hey, that's what makes this field so captivating. The line between science fiction and reality is constantly blurring.
And research like this is what's pushing that boundary. Every new discovery, every tiny optimization, it's another step towards that fusion-powered future.
You've got it. And speaking of optimizations, this research at JGT, they weren't just looking at the big picture, the long-term goals.
They were getting their hands dirty, figuring out the nitty-gritty details.
Precisely. They were laser-focused on finding ways to squeeze every last drop of performance out of their experimental setup.
Because even tiny improvements, they can have huge ripple effects down the line, right?
Exactly. It's all interconnected. And one of the things they focused on was how long they could sustain those high-energy conditions in the plasma.
We talked about how they achieved that record-breaking neutron rate, but how long did it actually last? Was it just a quick burst or...
That's the thing. It wasn't just a flash in the pan. They were able to maintain those conditions, that high rate of fusion, for several seconds.
Seconds? Hold up. Isn't that a big deal in fusion world?
It's huge. Right. Think about it. Most fusion experiments, they can create a plasma for a tiny fraction of the second, maybe a few milliseconds at best.
Right, like blink and you miss it kind of thing.
Exactly. But several seconds, that's an eternity in fusion research.
Yeah.
It means they're figuring out how to actually control and sustain these incredibly powerful reactions.
So it's like, yeah, starting a fire is one thing, but keeping it burning, that's the real challenge.
That's where the true potential lies. And that's what makes this research at JT so exciting. They're not just achieving fusion, they're taking those first steps towards making it practical, sustainable.
Because fusion power, it's not just about like proving it can be done in a lab.
It's about changing the world, providing clean, safe, abundant energy for everyone.
And findings like these, this is how we get there. One experiment, one discovery, one tiny optimization at a time.
Precisely. And there's still so much more to learn, so much we don't know yet. But that's what makes this journey so incredible. It's a journey of exploration, discovery, and pushing the boundaries of what's possible.
It really makes you wonder what other scientific mysteries are out there just waiting to be unraveled. What other seemingly small discoveries might hold the key to unlocking even greater breakthroughs? It's both exciting and a little bit daunting.
Absolutely, and that's the beauty of science. There's always something new to discover, always another layer to peel back.
And who knows, maybe someday we'll look back at this research on hydrogen optimization as one of those pivotal moments, those early steps that led to a truly revolutionary change in how we power our world. So we've been talking about these high energy tails, right?
Yeah, it's a pretty visual term.
But can you actually see them? Like, are there pictures of these deuterium atoms with little tails zipping around?
Well, not exactly. We're talking about things that are way too small to see directly, even with our most powerful microscopes.
Okay, so how do they know these high energy tails are really there?
We can visualize it, though, through something called a spectrum.
A spectrum? Is that like a rainbow kind of thing?
Kind of. Imagine a graph.
Okay, I'm picturing a graph.
And on one axis, you have the energy of the deuterium ions.
Got it. Energy levels.
And on the other axis, you have how many ions have that specific energy.
So it's like a snapshot of the energy distribution of all the deuterium in the plasma?
Exactly. And typically, without this high energy tail, the graph would look like a bell curve. Most of the deuterium would be clustered around a certain average energy.
Makes sense. Some higher, some lower, but most right there in the middle.
Exactly. But when they optimize the hydrogen and create this high energy tail,
the bell curve goes out the window.
It gets a little lopsided, yeah. Instead of smoothly tapering off at the high end, it extends out this tail representing those deuterium ions that now have way more energy than average.
So it's like the bell curve sprouted a tail, reaching for those higher energy levels.
A very energetic tail. And it's those high energy deuterium ions that are more likely to fuse releasing all that energy.
And this tiny tail on a graph, this is what translates into a massive leap for fusion power.
That's the incredible thing about this research. It's like finding a tiny switch that unlocks a huge surge of power.
It really makes you think, what other, seemingly small things could have a huge impact on fusion power? What else haven't we discovered yet?
That's what's so exciting. This is just the beginning. We're just starting to scratch the surface of what fusion power could be.
It's both exciting and kind of, daunting at the same time.
Absolutely.
Yeah.
But that sense of wonder, that's what drives us, right? The pursuit of knowledge, the possibility of a brighter future.
And who knows, maybe someday we'll look back at this research, this deep dive we took into hydrogen optimization, and we'll see it as one of those turning points, one of those little steps that led us to a world powered by fusion.
To clean energy, a sustainable future, all thanks to a deeper understanding of the universe and the power of scientific discovery.
It's an incredible thought. And to our listeners, thank you for joining us on this deep dive. We hope you learned something new today, and we'll see you next time.